Okay, welcome to this video for Worksheet 1 for numerical computing. So you should be taking notes on these videos and using your notes to help you with the worksheets. If you haven't already done so, please watch the syllabus video before you watch this video, and also make sure that Python is installed on your computer before you start working on the worksheet. Although you may be able to get through worksheet 1, but a lot of the worksheets will require you to have Python working. If you already have version 3.7, then you don't need to upgrade to 3.8. I do tell you to put the most current version on, but 3.7 and 3.8 are pretty much the same. So that's okay. If you're just behind by one version, should be fine. Okay, so this is the website for Python. When I say, sometimes in the homework I'll say do something by hand, check on technology, I'm not usually implying Python, although you're welcome to use Python. The types of things I'm imagining you'll use will be something like Wolfram Alpha, possibly Desmos, and if you go to Apps American EDU, you'll see that you have a whole variety of things available to you as an American University community member. And you can actually get MATLAB or Mathematica. By the way, to get to this particular page, you need to use Duo, and if you need help getting that set up, let me know, and if I can't help you, I will refer you to the help desk on that. But you can get into this page and you have access to a lot of things. Okay, you have access to Mathematica if you want it, not required. For the things we're doing in this class, other than Python, Desmos or Wolfram Alpha will be sufficient. Okay, so those are just some comments I wanted to make about that. Next, I'm going to talk about bracketing roots. Okay, basically you want to bracket roots between zeros. You already know this. Okay, so for example, if you have some kind of curve, there we go, an axis, and you happen to know that at point A, A on the x-axis, you know that your function is positive, and that somewhere at B, your function is negative. Then you know somewhere between A and B, there is a 0, provided all the things that you normally have to say in these situations, like my function is continuous, doesn't do crazy things. Okay, so there's at least one 0 in this domain. However, you know, I'm sure you know, that this isn't always that cut and dried. Sometimes we have multiple zeros. So for example, over here our function is negative, so at this point our function is negative, and then at this point our function is positive, and it only guarantees a single 0, but there could be, for example, 3 zeros inside that interval. So it would have to be, an odd number of zeros. Well, what does that mean in terms of what if you touch down and turn around? So the thing is, if you touch down and turn around, that's really considered to be 2 roots. So if you see as I move my axis, it's easier than moving the function. I still have 3 roots, 3 roots, 3 roots, and what about here? Actually, I still have 3 roots, but 2 of them came off as a complex conjugate pair. Okay, and right here I have 2 roots, but they're just, one is a double root. And then I could have this one here. I could say, well, I have 2 real roots, one of which is double. But fundamentally, the number of roots didn't change when I just moved that axis. It just threw 2 of the roots off into the complex plane. Okay? But in terms of just the real world, if we're just talking about the real world, we can hide zeros inside here. The other thing we can do is, what if you're looking at this interval? Okay, so it's negative, negative. So you could have an even number of roots. Well, 0 is an even number, but you'll have an even number of roots in that interval. So you could potentially have roots hiding where you think there's no roots. So that's something to be aware of. Okay, so that's enough for that topic. Shapes of zeros. I want to talk a little bit about shapes of zeros, meaning zeros is another word for roots. So if I have here my axis and I have a function that is just a line, that is the standard, typical, regular old boring root. Okay? That's a degree 1. It's a root or a 0. If I have something that's like a parabola, I might end up with what's a double root. And they're easy to keep track of because the shapes, that is, because they follow this pattern. It's just x squared, x cubed. I think of that as the prototypes for what the roots look like. So x squared, the function x squared, really is a second order root at 0. So you can just imagine what a parabola looks like. That's what a second order root looks like. What does a third order root look like? Well, it looks like x cubed. Okay, so you just draw x cubed. That's basically what it looks like, and that's what a third order root looks like. What would a fourth order root look like? Well, it looks pretty much like a parabola, but it's flatter. So I like to kind of draw them like that. I just try to make sure they come off flatter than a parabola would. Okay, and what would a fifth order root look like? It kind of does the same kind of thing. It's sort of flat. It looks very much like a cubic. But visually, you can't tell the difference between, say, x cubed. If you're going to do this by hand, x cubed, x fifth, and any odd power is going to look the same. Or first degree is obvious. It's just going to look like that. X cubed, x to the fifth, x to the seventh, etc. You're going to basically draw it like this, and all the other roots that are even are basically going to look like a parabola. So again, you're not going to really be drawing x fourth differently than that. It's more or less going to look like that. Okay, but just keep in mind that the multiplicities of these zeros or roots really manifest in the shape of the function that ends up resulting. Okay, now we start in on the calculus reminders. So now we're going to talk about calculus reminders. So first question is, how to find max value or min of a function. You probably know this, f of x equals whatever. Then what you do is you take the derivative of f with respect to x, and that's whatever else. I'm going to make more dots so you know it's not the same. You set it equal to 0, solve for x. That gives us potential extremes of f of x. So hopefully you remember all this, and then after you get your potentials, then what you're going to do is you're going to either go off in some kind of method to test it. You're going to possibly do, so then test using first derivative test or second derivative test, so on and so forth. Okay? Other things you can just do, inspect the graph, things like that. Okay, so just because you've generated potential maxes and mins doesn't mean your job is done. You know that you still have the rest of the work to go. Okay? Don't forget, f must be continuous at x in order for f of x to mean something. There's an exception and just one-sided continuity is, I'm not even spelling it, continuity is fine at the endpoints of your domain. Okay. Okay, next concept we want to go over is Rolle's theorem. Okay, so Rolle's theorem goes something like this. We're going to say you have some kind of axis to work with. Okay, you have some kind of function, and we're going to have, let's say, A and B. And if f of A and f of B are the same, well, I'm going to move this guy over because I meant for them to be lined up like that. If f of A and f of B are the same, then there's going to be some point where the derivative is 0. Okay, and we're going to call that point C. It doesn't have to be unique. Okay, and we know that f prime at C is 0, and that should make sense. If the function is completely constant, then of course, then f prime is 0 during the whole interval, and that's fine. But if it's going up and down, like if it goes down, it must go up again. If it goes up, it must go down again. So that should make intuitive sense, and I'm just going to sort of write this theorem down to make sure you know it. If f is an element of C, A, B, let me just sort of remind you or tell you what this means. Usually it's a curly C. You get C, A, comma, B. What this means, f is an element of the family of continuous functions over the interval A to B, where A to B is a closed interval. Mathematicians do not like saying things like that. They would rather just do a couple symbols that says everything in one little eye shot. So it's just really tedious to say all these things. But when you see this, you just mean, hey, it's nice. It's nice. It does what we need it to do. Like, it's kind of like a you know what I mean, but it's a very precise you know what I mean. Okay, and we want this to be differentiable. And if you forgot what differentiable means, you probably want to refresh on that interval. Okay, then if f of A equals f of B, then there exists a little letter C such that f prime of C equals 0, and C has to be between A and B. Okay, so that's Rolle's theorem. Hopefully that just seems intuitive, and honestly the very next one should also seem intuitive, and it's going to be the mean value theorem, and it kind of plays off of that. Alright, so we want the mean value theorem, and that says more things that I can't write without my pen. Let me just get back to the pen again. We have still an A and a B, and like lots of the words remain the same, but let's talk about what the theorem is trying to say, and then we'll pull it apart. Let's say we have a point A and a point B. We want to connect them. Okay. Then there's at least going to be one point. In this case there's two, but okay, there's going to be at least one point C where the slope, or the derivative, think of the derivative, the slope of the tangent line, at C has to match the slope of the secant line between A and B. Okay, so here's A, f of A, here's B, f of B, and C, f of c. Okay, so this theorem gives us that f is again an element of this continuous family of functions a to b and on the closed interval, and it's differentiable. Well, I wasn't as precise with my last definition as I should have been, because the interval on which it's differentiable is the open interval, even though it's continuous on the closed interval. Okay? Then there exists little c, where c is between a and b. Okay? That f prime of c is actually equal to that slope of that secant line. Again, I hope some of these things are just obvious. If they're not obvious, then come talk to me. These should all be refreshers, and they should all be obvious. Okay. Extreme value theorem. So the extreme value theorem happens, it says max and mins happen either where the derivative is 0 or at the ends of the domain. So I'm just going to type that for you. Extreme value theorem says max or mins extrema happen on continuous functions either where derivative is 0 or at the end points. Okay, and hopefully that is obvious to you. Okay, the generalized Rolle's theorem says if you have n zeros in a domain, f prime of x equals 0 at least n minus 1 times. This is kind of cool because this is this whole concept of something we call interlacing zeros. So every time you take a derivative, you get interlacing zeros with the other function. So if the original function had 10 real roots, take a derivative, now you're going to get 9 real roots, but they're going to be spaced in between the original zeros, and that's kind of cool. So you get this thing going. Okay, and we also have the intermediate value theorem. F is nice. In other words, it's continuous, etc. Okay? If f of a is less than capital K, which is less than f of b, then we know that some c exists so that f of c is equal to that capital K in that domain. Okay? So we know that it's essentially not much different than what we've been saying. We're just saying we have some kind of function. It's nice. And we have, f of a is here and f of b is here. Then it means we have to pass through all those values going from a, f of a is over here, and then like b, f of b is over here. That means we have to pass through all the values between f of a and f of b on our way there. Okay? Now it could go outside that range. Like, it doesn't preclude it going up and down. That's okay. It doesn't say it can't. But it means that at the very least you have to travel through all the points in between. Okay? All right. All that stuff. Hopefully it makes sense. Those things are really important to the underpinnings of calculus, and I just wanted to make sure that you guys were all up on that because some of these things we'll be referring to, and I just want to make sure you know what all the definitions mean, and you say, like, which theorem was that? Well, then they'll be in your notes and you can go back and that's what that theorem was saying. Okay, that kind of thing. Okay, now we're going to talk about the Taylor's theorem, and then after we talk about Taylor's theorem, we can talk about Taylor's polynomial. But I'm just going to underline Taylor there because we're going to talk about Taylor now. Okay, Taylor's theorem. What does Taylor say? Suppose f, now I gotta use my pen. Here we go. Suppose f is an element of this continuous set of functions, but now I'm changing the notation. C to the power n means it has continuous and it has derivatives, n of them. Like, yeah. I think it'll become obvious why I have to do that as this theorem starts opening up. Okay? All right, so we have as many derivatives as we need, and not only that, we have an extra derivative here. Exists on a to b. Then x naught is somewhere in that interval. We don't know where, somewhere. And for all x's that are in that interval, there exists some crazy value c, which depends on x. Like, seriously, it can't just be inside the interval. Nope, it has to depend on x that we picked. All right, fine. All right, between what? Between x naught and x, a lot of x's here, such that, okay, f of x equals capital P of n x minus capital R of n x. What do all these letters mean? Well, f of x is the function we would like to approximate using a polynomial, that we're going to use Taylor's polynomial. And we have Pn is the polynomial piece that's going to be approximating f. And this crazy thing is the remainder. This is the error or the remainder. Okay? And the remainder obviously has the same like characteristics of f. Like if you're trying to approximate like a polynomial, use a polynomial to approximate a sine function, you're going to end up with a sine function left over in the remainder, obviously. So you're going to subtract off polynomial components from whatever it is you've got. And so this guy, P of n, is completely polynomial. But whatever characteristics you had in f, you can't get rid of them by pulling off a polynomial. So all the leftover stuff gets chucked into the remainder. Okay? So far, we haven't said much. Okay? We're going to say more now. Okay, where? We're just basically labeling the pieces right now. The polynomial, and then n matters because n means the degree of the polynomial, so you'll see that's just yet another variable to keep track of. Okay, this polynomial starts off, we're going to put information. We have lots and lots of information at x naught, which is where our Taylor polynomial is going to be centered. So we're centering it at f naught. And we want to know the derivative at f naught. We want to know the function's value at x naught. And we want to know the second derivative at f naught. And you guessed it, we're going to want to know the third derivative at f naught, and we're going to want to know the fourth. We're going to want to know all the derivatives, honestly. As many as we can, and they're going to have this format. We put this in parentheses, the n in parentheses, and we mean don't raise the function f to the power n. What we mean is n derivatives, right? We want to know all the derivatives at x naught, and we're going to end up with this kind of expression. So hopefully you're familiar with this, and now we can say what form the remainder takes, and this is why you need that crazy c in the first place. We're going to say we're going to go one derivative up. We used n derivatives to get the polynomial in the first place. We're going to take one more derivative to try to figure out what's going on with this c. And honestly, there's a lot to be said about that c. Mostly we try to work around it, okay? Because that c depends on x. So what we really usually do is say, well, what's the worst thing that could happen? What if c is in the worst place possible? And then so we use that expression without really worrying about where that c is. We just know it's somewhere, so we just use it to say, well, the c is somewhere in the interval, so how bad can this derivative get? That's what we usually do with it. Okay? I like to think of this in terms of the word fox. I just like to think of the word fox. I think f of 0 and f prime of 0x, because it looks like the word fox. And that's how I kind of remember. But you know what? This is not always 0, right? But when x naught is 0, if x naught is equal to 0, we give it a special name. We call the Taylor polynomial Maclaurin. Okay? So hopefully that is nothing new to you. We're going to do some examples. Okay, example. Determine P2 and P3. Find, so I'm just going to say find P2 and P3 about x not equals 0. So it's just really Maclaurin for f of x equals sine of x. Okay, so we want f of x to be sine of x. And how do we do that? So I'm going to go ahead and pause this for a second so that I can write a whole bunch of stuff. Okay, so I just wrote down some derivatives of f. And so f is one of these, sine is one of these four functions, I guess, that goes on a cycle of 4. You go, derivative of sine is cosine, its derivative is minus sine, its derivative is minus cosine, and then you get back to sine again. So yeah, there's 4 functions in that set, pretty cool. But 2 of them are, just like negative of the other 2. So that's kind of a little bit cheesy, but anyway, that's what we've got, a cycle of 4. And so now what do we know? Because Taylor said we need to know all these derivatives at one point. So we are building an approximating polynomial based on a whole bunch of information piled up in one location. Later in this class, we're going to build interpolating polynomials where we don't pile all the information up on one x value, okay? So just keep in mind, Taylor is at one end of the spectrum where you pile up all your information in one place, and later we will spread out the information, okay? Okay, so I need to evaluate all my derivatives at the same point because that's what Taylor, or Maclaurin, is saying to do. Now, because we've got this sine and cosine thing here, this is pretty neat because sine, we know what sine looks like anyway. Sine kind of looks like this. And so it's actually, it's got this sort of, this odd thing going on. Because it's an odd function, half of these terms are going to fall out. We're going to get all the cosine terms because, okay, clearly I did this backwards. I drew cosine. Right. So here's sine. There we go. I didn't draw cosine. I got sine here, and sine is odd. Okay. So the point is I'm going to be getting I'm just going to be getting some of these terms. Okay, so we're going to put all these pieces together. It's easy to get confused. All right. So f, and this is my little foxy thing. F is approximately equal to f of 0 plus fox. I just think that's fox. F double prime 0 x squared over 2 plus f triple prime. Once I get the ball rolling, then I remember what's going on. Okay? And I've got another term, but I don't have to worry about it because that's going to wipe out at 0 anyway, so I don't really care. So I could just kind of leave that term off of my template. Then I'm going to dump everything in. So f is approximately equal to, forget this guy, forget this term. I need f prime of 0, which is 1, right? So this is just going to be 1. So I just need x. And then my x squared term is going to drop out, just like my x fourth term dropped out. And I'm going to get f triple prime, which is negative 1, x cubed over 6. So our final approximation is going to be x minus x cubed over 6. Okay? So hopefully that was not too bad. Okay, except for this small problem here, I actually didn't label which was which. I actually just found P3. So this part right here is P2. And then this whole part is P3. So P2 is just the x, and then P3 would be x minus x cubed over 6. Okay? So online we should plot f and P2 and P3 and compare. So I'm gonna bring that up online. Oh, I'm recording while I'm doing this. Okay, sorry to make you wait while I was doing that. I thought it was paused. Oh well. Okay, so here I have x and x minus x cubed over 6, but I also want to compare it to the original function, which is sine of x. And so Wolfram Alpha labels this nicely for you. Let's see what's going on. Okay, so the blue one is x, notice here, and then the red one is the next interpolating polynomial, and then the actual sine curve is kind of between them. It's kind of nice that way. So the signs, the S, I, G, and S, the signs will alternate, and so it's not surprising that you have one that's over, one that's under, one that's over, one that's under. That kind of thing is to be expected as you gradually approach your function. Okay? All right, next question. What is this crazy R thing that's going on? Like, what is this piece? What is this piece doing? Okay, so in this case, this is going to be a 4. And so this whole thing is just going to be sine of x, or sine of c of x. Let's just take this thing away and look at it. Okay. All right, so this thing is going to be 4 derivatives, but that's just going to be sine of x. And what is this? This is going to be a 4. And so this is going to be 4 factorial. Well, 4 factorial is 24, so that cleans it up a little bit. And, well, we're doing this at x naught is 0, so we don't need a lot of this other stuff hanging around. Okay? So when you're dealing with this kind of situation, we usually just cheat a little bit. It's not really cheating, I guess, but we just say can't go over 1. It can't be over 1. We do this a lot in numerical computing exercises for students. Okay, I have no idea if they do this out in the field, but this is stuff we do to build the conceptual framework. Okay, sine of x can't be over 1, and so then what we do is we look at this and we say, well, what x's are we concerned about? And if we're going from 0 to 7, then x could be as high as 7. So those are things you can think about. But in terms of your error piece, it's very common to just say sine or cosine can't be over 1. So then you'll do this kind of thing. You'll make some kind of bound on R, and you'll say R is less than or equal to x minus x naught. In this case, if we're using x naught is 0, it's going to be just x. And then you're going to divide by 24. Okay? So you can do something like that. And so then your remainder is still dependent on x, but you've kind of washed away that c, and it's a little more tangible. At least gives you an idea of what the boundary is. C is great in theory for proving things, but it's not really that useful for computations. right? Let me go back here now. So we talked about Taylor polynomials. Next we're talking about absolute versus relative errors. So some little things you're going to be asked on your worksheet. So if you want to calculate something, and you will actually not know exactly what your errors are, but we're going to calculate them a lot in homework because we're going to approximate functions that we know what they are, and so then we can actually find out how bad the error is. This is common, of course, in academics. You ask a question that you know the answer to, so you can see what's going on. Okay, so if you calculate something, and f is the actual function value, but your approximated value is f with a little hat. I'll call that f hat. So for example, maybe it's a Taylor polynomial or whatever. You just take the absolute value of the difference, and that's your absolute error. It's exactly what you think it would be. And your relative error is the absolute error divided by the expected. So it's just your same relative error. It's just like percent increase decrease formula. Relative error is just your absolute error. So difference over original, but original in this case means the correct value. Okay? A couple more little review items that, again, things you probably already know, and you just want to make sure these definitions make sense to you. What is chopping versus rounding? What is significant figures? Okay, so if you have a number, I'm just going to make up some crazy number here. Okay, and I tell you we're going to round to 4 significant digits. Okay, this would be 4 significant digits right here, 5, 2, 3, 9. Those are 4 significant digits. And there's a 4 afterwards, so I'm not going to round. I'm just going to leave the 9 alone. Okay? But if I say I want 4 digits after the decimal, then I would bring it up to here, 2394. So a 5.2394 if I want 4 digits after the decimal. And if I'm going to be rounding, I'm going to round that 4 up to a 5 because, of course, the 8 is 5 or greater, and that's the rule of thumb we use for rounding that up. Okay, so that's chopping versus rounding. And I do want to make a mention of significant figures. Again, the more scientific tool to use is significant figures, but it's a lot easier to communicate this idea of digits after the decimal. So if I'm giving you instructions on how to key in your quiz answers, I'm going to say, please use 4 digits after the decimal, or please use 7 digits after the decimal, because I just want to make sure that your answer gets recorded correctly. Those are just clerical instructions. I'm not thinking about it scientifically. I just want to make sure your answer gets accepted by the system. Okay? But if I'm talking scientifically, I'm more concerned about something like significant figures. I'm going to be counting all the digits in my number, and so it's a much more meaningful statement to say how many significant figures do I have. If I get rid of these, then I had 4 significant figures. Okay, but again, in terms of giving you instructions for keying in your homework into this Canvas, I'm going to just say like how many digits after the decimal, and that's also a common thing that people say. Okay, I think that covers everything I needed to talk about. Hopefully this recording works, and hopefully it makes sense to you. And thank you for being with me on this journey, this exciting journey of numerical computing. We have a lot of fun projects in the semester ahead, and a lot of fun homeworks. So we have a lot to look forward to. See you soon.